Section 7.3 is estimating a population mean. What you're going to find is there's a lot of similarities between estimating a population mean and estimating a population proportion. 7.2 is estimating a population proportion. We still have a point estimate. For the mean, the best point estimate for the population is X bar. We're going to assume here that our standard deviation is unknown. If the standard deviation is unknown, it's going to require a different distribution for us, not a normal distribution. It's something called a student's t distribution. The procedure we use has a requirement that the population is normally distributed or the sample size is greater than 30. Remember, if the original population is normally distributed, we're not as strict on that sample size being 30. We can use a smaller sample size. This is how we calculate the error with a t sub alpha over 2. T comes from a t distribution. It's called student's t, and it has n-1 degrees of freedom. S is our sample standard deviation. If sigma is unknown, we have to use the sample standard deviation. Now let's talk about what a student t distribution is. If the distribution of a population is essentially normal, then the distribution of this variable is a student t distribution for all samples of size n, and it's often referred to as a t distribution and is used to find critical values denoted by t sub alpha over 2. In this picture here, we can see a standard normal distribution. That's the blue curve. Everybody see the blue curve that I'm tracing out here? If you have a t distribution with a small sample size, let's say our sample size is 3, what you'll find is that's this gold graph right here. The tails are thicker. There's more error down here in the tails. The peak doesn't go up as high. So there's a little more error built in here with a small sample size. With a larger sample size, the t distribution gets more normal. You see the pink graph here represents a t distribution with a sample size of 12 or 11 degrees of freedom. So something that's different with the t distribution is that the shape will change depending on the sample size. With the normal distribution, the shape never changed. We always said it had that same shape, and it does, but with the t it's going to change depending on your sample size. So that's something different that we need to notice. Some important properties of the t distribution. The distribution is different for different sample sizes. It has the same general symmetric bell shape as the standard normal distribution, but it reflects the greater variability with the wider, thicker tails than what is expected with small samples. The student t distribution has a mean of t equals 0, just like the standard normal distribution has a mean of z equals 0. The standard deviation of the t distribution varies with the sample size and is greater than 1, unlike the standard normal distribution, which has a standard deviation of 1. So with the t distribution, it's going to change depending on the sample size. We know the mean is at 0, but we don't know about the standard deviation. That's going to change. As the sample size gets larger, the student's t distribution gets closer and closer to the normal distribution. Once you have a sufficiently large sample size, then you can use the normal distribution. But I'm not going to leave that up to you guys to make that judgment call. Whenever you're making an estimate about a mean, with the standard deviation unknown, use the t distribution. Now, if you go to your calculators and you hit second vars, you will see that there's a t distribution right here. The t PDF, the t CDF, we have an inverse t, just like the inverse norm. The t CDF, it acts just like the normal CDF. The only difference is we now have to add in another variable for the degrees of freedom or the sample size. The number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all the data values. The degrees of freedom are n-1. So mu is still the population mean, x bar is the sample mean, s is the sample standard deviation, n is the number of sample values, e is still our margin of error, and t sub alpha over 2 now is the critical value t, separating an area of alpha over 2 in the right tail of the t distribution. So just like with the normal distribution, we're going to draw a symmetric bell shape, and t sub alpha over 2 is going to be our critical value that separates this size of alpha over 2 on the right hand tail of the test. It's got to be a positive value. T-scores are like Z-scores. They're both positive and negative. And if we just use the inverse T, we would end up with a negative value. Just like with the confidence intervals for proportions, we have a point estimate. In this case, it's X bar. To calculate our confidence intervals, we take our point estimate plus or minus the margin of error. With the proportions, it was a p hat plus or minus the error. Here, how we calculate the error is we use our t sub alpha over 2, our critical value, times s divided by the square root of n. Remember, for proportions, we used for our confidence interval p hat plus or minus the margin of error, where e, our error, was equal to z sub alpha over 2 times the square root of pq over n. That was just our standard deviation divided by the square root of n. So there's similarities here. It's the point estimate plus or minus the error, and we have a formula for how we calculate the error. So the procedure for constructing a confidence interval for mu with sigma not known is to first of all verify that the requirements are satisfied. The requirements being that you have an independent random sample, that your sample is normally distributed, which means that your sample has to have at least 30 or come from a normally distributed distribution. And then we want to evaluate the margin of error and find the values of x bar minus the error and x bar plus the error, and then substitute those values in this form where we have our lower limit less than the mean less than our upper limit. Now, what a confidence interval is doesn't change. Remember, we have a population average, this value of mu. It doesn't change. We just don't know what it is. So what we do is we run a test and we come up with these lower bounds and upper bounds that we say capture that population proportion. Kind of like if this is our value of mu, we can create these different confidence intervals that may or may not capture the full value of our population parameter. Sometimes they don't, they just miss. So in this case, this would be an example of one that missed. A common claim is that garlic lowers cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. The changes in their levels of LDL cholesterol have a mean of 0.4 and a standard deviation of 21. Use the sample statistics of n equals 49, x bar equals 0.4, and s equals 21 to construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. So here we go. I'm going to show you how to do this on the calculator. We're not going to do this by hand. In order to do this on the calculator, the first thing you're going to do is hit the stats button. We're going to do a test. And the test we want to do is a T interval, which is at number 8 here. We don't have the raw data, so we're going to unhighlight data and we're going to highlight stats. Stat means the summary statistics. So when I highlight the summary statistics, you see it has a place here for us to put in x bar, where x bar is the mean. And we were told that we have a mean of 0.4. We have a standard deviation of 21. And our sample size is 49. Our confidence level, were we told? Yes, we were told a 95% confidence level. This is what the input screen looks like. And we're going to hit enter on the calculate part, and this is the output. So our confidence level here is from negative 5.6 to 6.4. Based on this confidence interval, what does this suggest about the effectiveness of garlic in reducing the LDL cholesterol level? Why do I say this doesn't change the cholesterol level? If 0 is in that confidence interval, then there's essentially no change. Let me put this up here. We hit stat, go over to test, and then down to T interval. Remember, this number measured the change in their LDL level, meaning they measured the cholesterol before they did the test. They administered the test of giving people raw garlic, and then they measured their cholesterol again. And this mean here is on the average change in the patient's cholesterol level. Because 0 is almost right smack dab in the middle of this, it doesn't matter where it was. If 0 is in the interval, then we can't assume that there's been any change. So based on this confidence interval, garlic appears to not change the mean LDL because 0 is in there. If 0 is in the interval, then there is no change. It's easier to do the confidence intervals on the calculator. I'm not going to require you to do them by hand using tedious computations. That's why I wanted to show you how to do this using the calculator. On your input, you have a choice of either using the summary statistics. That's what this stat means right here. This is the summary statistics. And if you use data, you would actually have the data in a list. We were provided with the summary statistics, the mean and the standard deviation and the sample size. So that's why I highlighted stat there as opposed to data. Finding a sample size for estimating a population mean, it's just like the formula. If the population standard deviation is known, then we're going to use this formula. In order to use this formula, the standard deviation would have to be known. So assuming that we want to estimate the mean IQ scores for the population of statistics students, how many statistics students must be randomly selected for IQ tests if we want a 95% confidence interval that the sample mean is within 3 IQ points of the population mean? Well, here, because it's a 95% confidence level, that means alpha is 0.05, so alpha over 2 is half of that. Z sub alpha over 2 then would be 1.96. How do you get the Z sub alpha over 2 if you don't know what it is? Inverse norm 0.025. And then your error is 3 and your sigma is 15. Just plug those numbers into the formula and we would get n is equal to 1.96 times sigma, which was 15, divided by 3, and we would square the whole thing. So this is open parentheses because we got to square the whole thing. 1.96 times 15 divided by 3, close the parentheses, and then square. So we need to survey or sample 97 people. Any questions? Finding the point estimate and error from the confidence interval. This is exactly like what we did before for the p-hat. Now we're doing this for x bar. In order to find the point estimate of the mean, we would use our upper confidence limit plus our lower confidence limit and divide it by 2. Because remember, on this confidence interval here, if this were a number line, we would have our point estimate right smack dab in the middle. The error here would be the same to the left and to the right. So this number right here would be x bar minus the error. This would be x bar plus the error. In order to get p, we just need to average these two numbers together to get the number that's in the middle. This is a formula for an average. Add the two numbers together, divide by 2. To get your margin of error, we would take this upper limit minus the lower limit and then divide that results by 2 because we have 2 times the margin of error here. So for example, our upper confidence limit here is x bar plus the error minus the lower confidence limit, that's x bar minus the error, divided by 2, because when we do this we would have to distribute that negative here, and that would give us x bar plus the error minus x bar plus the error divided by 2, and we would see, well, these cancel out and we have 2 times the error, and when we divide that by 2 it just gives us the margin of error, which is what we were looking for here. So these are just mathematical formulas that you can add to your formula sheet. And then the round off rule for a sample of size n, if the computer sample size n is not a whole number, round the value up to the next large whole number. That's why I said up here that we had to use 97 even though the calculator gave us 96.04. We have to round up to the next whole number whenever we're calculating the sample size. When finding the sample size n when sigma is unknown, what you want to do is approximate the standard deviation by taking the range of the data values divided by 4. This section presents methods for estimating a population mean, and a difference to knowing the values of the sample data or statistics. We must also know the value of the population standard deviation. If you know sigma, this is different from what we did before, then we can use a normal distribution and we're back to our familiar z-scores. So that would be a z-interval on your calculator. So you would hit stat, go over to tests, and then go down to z-interval for your confidence interval. If we know sigma and we're estimating a population mean, it still has to be a simple random sample. The value of the population standard deviation has to be known, and either the population, the original population, is normally distributed or your sample size is at least 30. So for a confidence interval for estimating a population mean with sigma known, we go through the exact same process, but now our error is calculated using a z-score. So we can use a normal distribution, not a t-distribution. Example, people have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably, so we need to update our estimate of that mean so that boats, aircrafts, elevators, and other such devices do not become dangerously overloaded. Using the weights of men from a random sample, we obtain these sample statistics for the simple random sample. N is equal to 40, so that's our sample size. X bar is the average from the sample, 172.55 pounds. Research from several other sources suggests that the population of weights of men has a standard deviation given of sigma equals 26 pounds. So here sigma is known. So our best point estimate for the mean weight of the population of all men is going to be that 172.55. Part B here says construct a 95% confidence interval estimate of the mean weight of all men. We do that on the calculator. So we do just what I said. We're going to go to Stat, Tests, and we're looking for a z-interval, which is number 7. We don't have the list of data. We do have the summary statistics. This is our input screen. Now we put the information in. What are we going to use for sigma? 26. What is x bar? And n? We want a 95% confidence level. So we're going to calculate this, and it gives us this output. So our confidence interval is 164.5 to 180.6. What do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger capacity of water vessels in 1960? Is it okay? It's in the confidence interval, isn't it? So it should be okay. Because lives are on the line and this number was at the low end of the confidence interval, it might be worth it to adjust the average weight up some. All right, to determine when to use a t-distribution or a z-distribution, the first thing you want to do is ask yourself, is the standard deviation known? If the answer is yes, is the population normally distributed? If it's yes, then use the normal distribution. If it's not normally distributed, is your sample size bigger than 30? If it is, then use the normal distribution. If it's not, then you have to use a bootstrapping method, which you guys can't do. You need software to do it. It goes beyond the scope of this course. If the standard deviation is not known, you need to still ask yourself, is the population normally distributed? If it is, use the t-distribution. If it's not, as long as the sample size is sufficiently large, you can still use the t-distribution. Otherwise, you have to use the bootstrapping methods, which comes integrated with software such as SPSS.